You know that big chart in every science classroom, the periodic table? For a lot of us, it just looks like this, well, a confusing mess of letters and numbers, right? But what if I told you it's not something you have to memorize? It's actually a map. A map that can unlock the secrets of literally everything in the universe. So come on, let's unfold this thing and start exploring.
Think about it. Every single thing, the hydrogen in the water you drink, the oxygen you're breathing, the gold in a ring, it all has a specific address on this map. And just like a real map, where an element lives, its location, tells you a ton about its neighborhood, and, get this, its personality.
So, here's our game plan for reading this map. First, we'll get the basic geography down. Then, we're going to take a journey across the rows. After that, we'll meet the element families in the columns. Then comes the fun part. We'll crack the secret code that runs the whole thing. And finally, we'll use that code to start predicting how these elements will act.
All right, first things first. Let's get the lay of the land. You gotta understand, this map isn't just a random collection of boxes. Nope. It's built on a super strict, really logical set of rules. And that's what makes it so incredibly powerful.
Okay, the entire geography of this thing boils down to two main ideas. You've got the horizontal rows, those are called periods. Think of them as telling you how many layers or electron shells an atom has. And then you have the vertical columns, the groups. These are like families. Everyone in the same column has a really similar chemical personality.
And the reason this whole system works is because of something called the periodic law. It sounds fancy, but it's a really simple and kind of profound idea. It just means that as you move along and add more protons to an atom, its properties, they change in a predictable, repeating pattern. And that's the periodic part of the periodic table. It's all about those repeating patterns.
Okay, so what actually happens when we travel along one of those horizontal rows? Let's take a little trip across a period, and you'll see just how dramatic the changes really are.
We're going to take a little road trip, let's say across the third row of the table. That's period 3. We'll start way over on the left with element number 11 and go all the way to the right to element 18. So, our journey kicks off with sodium. It's a classic metal from group 1. And its personality? Well, it's explosive. Seriously, this is the kind of element that goes absolutely wild when it touches water. All it wants to do is get rid of an electron. Now, by the time we get all the way to the other side of the row, we run into argon, over in group 18. And its personality is the total opposite. It's a noble gas. It is completely stable, super chill, so non-reactive that it literally just hangs out in the air, not bothering a soul. So that trip from explosive sodium to chill argon, that pretty much shows you the trend you'll find in every single period. As you move from left to right, elements become less and less like a metal, their atoms actually get a bit smaller, and their personalities go from super reactive to completely inert. It's like a spectrum.
Okay, so that's the horizontal journey. But what about going vertical? Let's see what happens when we travel down one of those columns or groups. This is where things get really interesting, because this is where we meet the families.
Right, so like we said, a group is just a vertical column. And the reason we call them a family is because they all share this really strong resemblance. Not just in how they look, but, and this is the important part, in how they act, chemically speaking.
So let's meet a few of the most famous families. Over in group 1, you've got the superreactive alkali metals. That's where our friend sodium lives. Then way over in group 17, you have the halogens, which are known as the salt formers. And of course, in group 18, we've got those noble gases again, the totally non-reactive elements.
Okay, so we've seen that these patterns exist, right? We see them going across the periods and down the groups. But now it's time for the big reveal. The big question is, why? Why do they exist? It's finally time to crack the code.
I mean, this is the question, isn't it? Why are all those alkali metals in group 1 so much alike? Why do all the halogens in group 17 act as salt formers? What is the secret ingredient that ties them all together?
The secret. It all comes down to something called valence electrons. Okay, what are those? They're simply the electrons in the very outermost shell of an atom. You can think of them as the frontline soldiers in chemistry. They're the ones that get involved in all the action, in all the chemical reactions. They basically determine everything about an element's personality.
And here's the best part, the simple, beautiful secret. The group number is the code. Just look at group 1, the alkali metals. Every single one of them has exactly one valence electron. Now check out their neighbors in group 2. What do you think? Yep, they all have 2 valence electrons. It's right there in the number.
See, all of chemistry is really just about how these outer electrons interact with each other. And since every element in a single group has the exact same number of them, they're all going to react in a super similar way. That's the family resemblance. It really is that simple.
So now that we have the code, valence electrons, we can actually use it. We can use it to understand and even predict all those trends we see across the entire map.
Okay, let's take atomic size. When you move across a period, you're adding more positive charge to the center, to the nucleus, and that extra charge pulls all the electrons in a little bit tighter, which actually makes the atom shrink. But when you move down a group, you're adding a whole new shell of electrons, kind of like adding another layer to an onion. So naturally, the atom gets bigger.
And you know what? This same logic explains why things are more or less metallic. Being a metal really just means you can lose an electron easily. So, as you go down a group, that outermost electron is way farther from the center, making it easier to let go of. That's why elements get more metallic as you go down. But going across a period, that center nucleus gets stronger and holds onto its electrons tighter, which makes the elements less metallic.
So why does any of this matter? Here's the deal. The periodic table isn't just some dusty old chart for organizing things. It is one of the most powerful predictive tools in all of science. Seriously, just by knowing an element's address, its period, and its group, you can instantly figure out its core chemical personality and make a really good guess about how it's going to behave.
And this incredible predictive power, it's not a new thing. Back in 1869, this guy Dmitri Mendeleev was so sure he was right about the table's logic that he actually left blank spaces in it for elements that hadn't even been discovered yet. He used his map to predict what they'd be like, and years later, when they were finally found, his predictions were spooky accurate. Just amazing.
Which, brings us to today. The 7th row of the table is now officially full. But scientists are working right now, pushing the boundaries to create new elements for an 8th row. So, I'll leave you with this final question. Using the map we've just learned how to read, what can you predict about the very first element